Hey, g'day, it's Prezzo, thanks for stopping by. Now, it's January in 2025 and I'm back working on Threadexpress version 3, and there is a playlist. The link is up above there now. If you're not familiar with the project, you can go back and see the first 3 episodes of this build series. Now, Threadexpress is an accessory that fits onto a milling machine, and it allows you to cut any pitch or any diameter thread, both internal and external, using a simple shop-made fly cutter. Now, today's job is to make up some parts for the headstock of this unit, and I want to get that mocked up and maybe do the pinion drive for this spindle, but let's have a closer look on the bench. So this part here is a combination of a lead screw and a spindle for Threadexpress. It's driven by this bevel gear here and a pinion, and it carries bearings top and bottom. And this allows you to fit either an ER32 collet chuck or a standard 3-jaw chuck, a 4-inch chuck. And this allows you to grip work and rotate it, and also move it along the pitch ratio that you set on the machine while you fly cut the thread. Now, with these 2 aluminium castings here, I need to bore these out to suit the bearings, both top and bottom. And then we're going to add some aluminium side plates to these to mock up the headstock. So I'm going to go over to the milling machine now. We're going to bore out this smaller diameter here to clear the shaft, and then we'll do the recess for the bearing. Got 2 of these parts to do, and I've used my touch probe to find this edge and then offset the correct distance to the center of the bore. Done the same thing on the center end Y, and I've got my vise stop there, so as soon as I'm finished this part I'll swap out the other one, and hopefully they're going to be concentric with each other when they're top and bottom on the headstock. Now, I'm going to do the inside diameter on this one, 44.5, and I'll do the outer diameter on the lathe. Now, the reason for that is that I don't have a boring and facing head, just a boring head. And if I get this accurately bored, I can use that as a reference when I go over the lathe. But yeah, ideally you do everything here in the milling machine in one setup, but yeah, don't have a facing head. Okay, it's going to be a bit tedious, it's going to take a while. I'll bring you back when I'm fairly close. So we're 0.98, just under a millimetre undersize. The diameter of this bore is not really critical, it's just clearance for the spindle. So I'm just using a telescopic gauge here and my caliper to get the dimension. If this was really critical, I'd put a dial indicator on the boring head, and I've actually got one. My good friend Roger Taylor from the United States sent me one, and I made a sort of a clamp that goes on the boring head. Bit of a fiddle to set up. I don't really need it for this bore, so I'll just use the caliper. So I'm going to take the finished pass on this now, and then I'm going to see if this top diameter here is going to clean up. I'm a bit worried that the bore that I just made is not concentric with this chord hole. Now, these were castings that I made. If you were doing this, and you didn't have foundry equipment, you just made this out of solid plate stock. I was just trying to save money by doing it out of a casting. But that's the issue that you have when you do a chord casting. You've got to be fairly sure that the core is in the right place. I think it's going to be okay. No, you wouldn't read about it, would you? That's close enough. I'm just giving this a skim cut to see if it's going to clean up to the correct dimension, which is 52. And still got a way to go on this face here, but I think it's going to be okay. So we're at 50.25. There's still a bit to come out of that other side there. Gee, it's going to be close. Anyway, I'll do this on the lathe. You sort of see how far I've got to go there. Okay, same process on this one here. Dimension for the inner bore on this one is 50 though. Right, that was the last cut on that one. Nice finish for a casting too. Okay, I'm going to go out the lathe now and we're going to try and get the outer bearing fit. Alright, I've got that set up in the forge jaw now, and that's running to within about 200ths of a millimetre, that's less than a thou. So I'm going to bore out this outer diameter here to the correct depth of the bearing. So that's not boring out to the full diameter yet, but we're really close. So I just want to measure this to get some idea of where I'm at. This is not an accurate measurement. So 66.64, I'm going to finish at 68, so I think that's going to clean up fine. Okay, I just measured that with the micrometer and we're at 67.56. A little tiny bit of the casting hasn't cleaned up, but that's going to go. So I'm going to bring this out to just under 68 and we'll try the bearing. With the caliper it says 67.81, my DRO says exactly the same. So I'm fairly confident we're cutting to size. I have got a micrometer I'm checking with as well. Okay, that's 67.97. And I checked the bearing at 67.98. So that'd be an interference fit, but I don't want that. Yeah, probably looking at that and saying, yeah, that's a loose fit. But don't forget that when this is all assembled, the split nut is going to take up the clearance in the bearing. It's going to hold it in place. There's no heavy loads, it's not rotating at high speed, so it's going to be fine. I'll put some grease around the outside of the outer race. And what I need to do now is just sort of go in there with a sharper cornered insert because the one that I used had quite a large nose radius. I'll do the other one off camera, it's the same thing, and then we'll try assembling this and work out how big the side plates for the headstock need to be. Okay, so that's the second one done, and it just slides in there really nicely. It can be a little bit difficult to get out if you get it sort of skewed. And looking at these, say, well, that's turned out perfectly, but let me show you something that made me quite sad. It didn't quite clean up where that core was, but it did clean up right on the outer edge, so the last 3mm and the bottom 3mm are machined to the full diameter, so that's okay. If this was some sort of high revving turbine engine, yeah, you'd worry about it, but in this situation it's going to be fine. So I'm going to take these out of the chuck, and then we'll try mocking up the spindle inside the bearing bores, and we'll sort of work out where these side plates, or at least what dimensions they need to be, and I'll check against the drawing. I've done it on the 3D model, but you always want to check it for real and make sure everything sort of lines up. What I've done here is I've mocked up this headstock assembly. Now, just after machining out the bores for the bearings, I sort of assembled everything on the bench. But then I wanted to be sure that these side plates, which locate the two end plates, were actually correct. So rather than cut up a lot of expensive aluminium sheet stock, I laser cut mock-ups of these side plates. Now I did that directly from the geometry on the CAD model. So these shapes here were exported as DXF files, and I cut that out on my laser cutter next door. Now plywood's cheap and expendable, you can throw it away if it's wrong, but once you start cutting up expensive sheet stock, you want to be sure that everything's correct. So what I've been able to do is to verify that I can take the backlash out of that screw, and you can see there is some backlash there now, but when we tighten up the split nut on this end, that takes up all the play, gets rid of the backlash, but everything still rotates freely. So that part of it's good. Now I've also mocked up the pinion drive for the bevel gear. Now this is just the stock bevel gear that I bought on AliExpress, but what I've done is I've shortened this shoulder by 2mm here. I've drilled and tapped an M5 threaded hole for a grub screw to hold that onto the shaft, and I've got my bearing. There'll actually be two bearings on this, and I was able to put that through the hole in the side of this plate here and just verify that everything looked correct. So I'm fairly happy with that. I think we're ready to go ahead now and cut out the aluminium stock for these side plates, and then I'll machine up this casting and fit the bearings for the pinion drive and so on. But yeah, always mock things up if you can. It's a lot easier to fix things at this stage if you notice that there's a problem. But I think everything's correct. I may have to enlarge this hole here just to give me some adjustment. But yeah, I think we're good to go. And that's the problem with having a miniature bandsaw. Oh well, jigsaw it is. Okay, get this milled up square. I don't really have any square edges or straight edges on the stock yet, so I've mounted it on a fixture plate in the vise. I've just clamped it down there, and I'm going to skin this back face here, and then I'll cut the other long edge parallel to that by setting it up the same way and just sort of running an indicator along the machined edge, and then I can side mill the two ends. It's amazing what you miss sometimes. So the plan was to unclamp this stock, flip it around, machine this rough edge on the back side of the fixture plate, and then I realised that all I had to do was to move across on the DRO the correct finish dimension that I need, plus the diameter of the cutter. Now I've done that, and that means I don't have to break down the setup, I don't need to change anything. I will have to move the clamps though, and I'll do that now. And I can machine this front edge, but I didn't leave enough clearance at the front here, and I don't want to cut into my fixture plate, so I've got the cutter set just 0.1 of a millimeter up off that surface there, it'll leave a little lip, but I can file that off later. But yeah, it's just one of those cases where you don't think it through properly, but we'll get it right. Okay, we got two parallel edges now, and that's my correct width across there. So now I can side mill the two ends and bring it back to length. Okay, I've offset 208 plus 16 the diameter of the cutter, and I can machine this other edge now. Once again, don't have to change the setup. Okay, I just took these plates out and checked them for dimensions, and they are correct. And while I was inspecting them, to my horror, I realised that there's one corner there that didn't quite clean up. And it's one of those cases where you've got a camera in the road. I should have really stuck my head in the way and checked that, but I was just looking at the camera monitor and it looked okay. But yeah, what can you do? It's going to be covered up by the end plate anyway. Now I've got some mounting holes to drill in these now. I'll do it in this machine, and I'll set an end stop here, and that way once I get touch DRO set up to do all my hole positions, I can just swap the parts and repeat that process. So let me get that set up and we'll drill the holes. One of the things I love about touch DRO is the ability to be able to map out hole centers and then to recall those hole positions as you move around the part. Now on the screen there you can see there are a total of 8 positions. This one in the top left hand corner here is the origin. That's the left hand edge of the part and the back corner, and all of the other centers there are holes that have to be drilled. So the 4 in the 4 corners there, they are the mounting holes, and then these 3 holes here are for the casting, which drives the pinion. So there's a point list down this side of the screen here, and as you move the spindle over each of those hole centers, the XY display here will count down to 0 as you go over each center. Now you can just move around indefinitely as long as you like, so you could actually spot drill all of the holes first, then go back and drill them out to whatever diameters you want, then you could tap them and so on. Just for accuracy, I'll probably drill or spot drill and then finish drill each hole position as I go. So just a feature of touch DRO, and as you learn to use that system, it enables you to do quite complicated geometry on your parts and get consistency between parts. When you go drill the mounting holes in this plate here, there are 4 of them in the 4 corners, and these will have an M5 socket head cap screw to attach this plate to the casting on the ends of the headstock. Now there are a couple of ways of doing this. You could buy shoulder bolts to ensure that this is accurately positioned when you screw everything down. You can also sort of make a, I don't know, like a shop-made type shoulder bolt. So what I've done here is I've got an M5 button head socket head screw, and I've drilled this out to 13/64 and then use a counter bore for an M5 socket head screw. And it turns out that that button head screw is actually a really tight fit in that hole. So as you drive the screw down, it sort of positions the plate really accurately. Now another method would be to just drill oversized holes and then assemble everything, check it, make sure it's square, and then put a dowel pin or a roll pin in a couple of strategic places to ensure that when it goes back together every time it's always the same. Now that's probably the method that I'll use here. The only problem with this method here is that if you get one hole position wrong and then try to assemble it, things will bind up and it just won't go together. If you put a roll pin or a dowel pin in later as a register, you can ensure that all your hole positions are correct, and you can modify them if necessary. And then as you put the dowels or the roll pins in, that ensures the consistency when you assemble later. So I think that's what I'll do, but that's an alternative if you trust your drilling technique. Never seems to work out for me, but that's an alternative. Okay, they're the 4 clearance holes with the 4 corners. Now I've got to do the 3 down the other end for the pinion drive. Now these 3 are less critical, so I'm just doing these all spot drilling in one go, then I'll come back. This is the tapping size for M5. Okay, I think you get the idea. I'll bore that out off camera, I'll do the other one, and then we'll do a trial assembly. Just going to machine up this little casting for the pinion drive housing. None of the dimensions on this are really critical except the internal bores, so a lot of the machining is just really cosmetic. Yeah, so we've got to make sure our bearings are a good fit and we've got clearance through the centre for the shaft. Yeah, so that's going to be a light press fit. I'll leave it there. Okay, flip this round, I'll do the other side. Made up this aluminium mandrel here so that I can mount this part and keep it concentric while I machine the other bore for the bearing. So I'm just going to use a spot of super glue to hold this together. Don't need a lot. If you overdo it, it can be hard to get off later. Let's put a couple of spots on there, that'll be plenty. So I'll let that cure, I can face it off, do the bore for the other bearing. The other bearing needs to be recessed quite a lot. That's to provide clearance for the boss on the pinion. Okay, this can come out now, and I've got to machine some slots to mount this to the side plate. Now I'm extremely pleased to report that this all went together exactly as I planned it to. It doesn't always happen, but sometimes you get lucky. And I did drill the castings on the milling machine just using the same setup that I did for the side plates. So I used touch DRO and an end stop in the vise so I could position each part, and I just set my 2 drill point positions up in touch DRO and just kept swapping the parts out. And when I put the side plates over the top of the castings and ran the screws through, everything just lined up. So very, very happy. So I've also done the pinion drive assembly, so that's all together now. Not completely finished. I haven't pushed this bearing in all the way yet. I want to get all of the finishing work done on the casting, and I'll press that bearing in right at the end. Could be hard to get it out otherwise. And I did have to put a bush in the hand wheel. When I bought this, it was fitted with a keyway and a 12mm bore. I needed a 10mm bore, so I just bored that right out in the lathe, got rid of the keyway and made an aluminium plug to go in there. And I've got an M5 grub screw holding that onto the shaft, which will be perfectly adequate. Now I do need to make a proper handle for this at a later stage, so this will have one of those sort of rotating aluminium handles, so it'll spin on this M6 socket head screw. But that's all spinning nicely now. So let me put this in place. I'll bolt it in place through that hole there, and I'll just show you how that works. Okay, you see that there are 2 screws holding this assembly in place, and there is some lateral adjustment there. So the idea is that you slide this down until you feel the pinion against the bevel gear. You set that so it has the correct mesh, and then you can lock that in place. Okay, let me show you inside. So you can sort of see the pinion protruding through the side of the headstock there now, and that's able to drive that larger bevel gear. And then of course later on that's also going to drive the lead screw. Now I haven't yet locked the bevel gear against the lead screw. I'm still discussing that with Cliff. We're trying to work out the best way to get a really positive engagement between the large bevel gear and that lead screw. Now later on you may want to use this as an indexing and milling attachment, and there will be a pin in the bottom of the headstock housing here, and it will engage in 12 or 1 of 12 holes in the bottom of that bevel gear, and it means that you can lock the spindle in a position and do some sort of milling operation at the top here, and then index it around either 2 or 3 or 4 holes, and allow you to do sort of geometrical features on a part held in the chuck. Now the milling forces or the cutting forces tend to make that joint slip between the bevel gear and the lead screw. So you need more than just a simple grub screw arrangement there. So we're trying to work that out. I've just left that for now. And you can see here that the whole lead screw is rotating. Well, let's turn that around. So we're able to rotate the lead screw around. And I'd like you to imagine there's a nut sliding up and down this lead screw, and as you rotate the handle, not only does the work rotate, but the whole headstock arrangement is going to slide along a set of linear rails. And that's the magic ingredient in this machine. So the mechanism, which we'll reveal later, allows you to control the movement of the headstock against the rotation of the lead screw. And that allows you to cut any pitch thread. Now in the next episode I'm going to start work on that linear rail assembly and try and get that part of it complete. There are still a lot of operations that I haven't done on this yet, and you know, just for now I wanted to make sure that I got this part of it right. I'm satisfied that this is all correct, and I'm checking the drawings as I go and making any alterations as I work through the parts. So next time we're going to do some of that more interesting stuff on the build. So I'm going to invite you to come along and watch that. Now, I've got some wildlife footage to show you today, and then we'll see you on the next episode. So it's Presso signing out for now. Cheers.